In this video, I'm going to be talking about some Taylor series problems, including interval of convergence, kind of manipulation of known Maclaurin series. What else? We got a bunch of stuff. Oh, figuring out derivatives based on a given Taylor series. Figuring out a Taylor series based on given derivatives. Something like that. Okay, so let's start with the interval of convergence of a Taylor series. Okay, so when finding the interval of convergence, I'm asking you to recall that we use the ratio test to determine the interval of convergence. They ask you find the values of x for which the series converges. That's going to be the first thing to do. You're going to use the ratio test. You're going to set up the limit of the ratio. You're going to compute the limit. You're going to do some analysis on the endpoints, and then you're going to get an interval. Okay, so let me just write down a quick example. Okay, let's look at the sum from n equals 0 up to infinity of -1 to the n, x to the 2n divided by 2n factorial. And anybody recognize this one? This one is one that we actually know what function this is, but it's cosine. Okay, good for you. If you can recognize this already, you're doing a good job. That's something that takes a while. It's easy to remember, okay, cosine's an even function, so it's going to have all the even terms, but seeing it looking like this and saying, oh, this is cosine of x, that's a little more difficult. So what we're going to do is we're going to set up the limit of the ratio of successive terms. And that will be the limit of -1 to the n plus 1, x to the 2n plus 2, divided by 2n plus 2 factorial, times 2n factorial over x to the 2n. And I'm going to need a little more space. There we go. Okay, now I have neglected to put on the -1 to the n plus 1 and the -1 to the n because when I take the absolute value of these things, it's not going to make a difference anyway. It's going to take anything that was negative and basically nullify that. So what we're going to do is I'm going to kind of expand this and start to cancel some stuff off. Okay, if I have x to the 2n under x to the 2n plus 2, well, I can cancel all but 2 of these powers, right? Okay, I've got x to the 2n, but I will be left with 2 powers of x. So I'll have x to the 2 in the numerator. And then 2n divided by 2n plus 2 factorial, well, all of the first 2n terms of 2n plus 2 factorial will get canceled off, and I'll be left with 2n plus 1 and 2n plus 2. And as n goes to infinity, this thing goes to 0, no matter what x is. Okay, so this is equal to 0, which is less than 1. What is the conclusion that we're supposed to make when we do the ratio test and the limit comes back less than 1?
It converges absolutely.
Converges absolutely. Okay, and it seems like it is converging absolutely and doesn't care what value of x you're using. Okay, so the Maclaurin series for cosine x converges absolutely for all x. Right? You could do the exact same thing with the Maclaurin series for sine x, and that might be a good exercise, but actually, maybe not. This one just comes back 0, and so it's not that exciting. What I would say, can anybody think of one of the 4 Maclaurin series that we know for sure isn't going to converge for all x? E to the x, maybe. 1 over 1 minus x for sure because it's geometric, and we already know there's rules about these geometric things. We need that common ratio to be less than 1. So I think that's what I want to do, is I want to try that and verify what we already know, that it's only going to converge for x between -1 and 1. Let's do that. Okay, so we know the Maclaurin series for 1 over 1 minus x is x to the n. Just geometric with first term 1 and common ratio x. Okay, well, we'll do the ratio test, and we'll take the limit as n goes to infinity of a n plus 1 divided by a n absolute valued. And really, this is the limit as n goes to infinity of the absolute value of x, because all but one of the n's will cancel. Well, as n goes to infinity, absolute value of x doesn't really care what's happening as n goes to infinity, so this is equal to the absolute value of x, which we need to be less than 1. And we know that the absolute value of x is less than 1 between -1 and 1. Now let's check the endpoints just to make sure. Okay, x equals 1. We have the sum of 1 to the n, which is adding together a bunch of 1's, which is certainly going to diverge. And at x equals -1, we'll have the sum of -1 to the n, so that'll be kind of alternating. It'll be 1, -1, +1, -1, +1, -1. And while that is not like diverging in the sense that it's going to infinity, it is not converging either. And so we say this diverges as well. Okay, now we're going to talk about manipulating known Maclaurin series. And I'll just start with one. This is very similar to one we did last time. I kind of got y'all started thinking about this because I figured, we had a long lesson yesterday or last time, and it was definitely something that we could start thinking about. Y'all seemed ready for it. So I might ask you to write the Maclaurin series for cosine of x squared. Well, we know that cosine of x is equal to 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial minus x to the 6 over 6 factorial, and so on. I'll write the general term, -1 to the n plus 1. No, -1 to the n, because we're starting at 0. Always mess that up. Divided by x, or x times x to the 2n divided by 2n factorial. All right, well, what I'm going to do is I'm going to replace x with x squared. So all of these are going to get replaced with x squared. All right, so cosine of x squared is 1 minus x squared squared over 2 factorial, x squared to the 4 over 4 factorial, x squared to the 6 over 6 factorial, and so on, plus -1 to the n, replacing x with x squared to the 2n, divided by 2n factorial. Okay, the factorial number isn't changing because it didn't really have anything to do with x. Right? This would be certainly a safe place to stop, say on a quiz or on the free response section of a test. But what if it was multiple choice and we had to recognize the right form of the answer? We would need to take this a little farther. We know how to take x squared to the 4th or x squared to the 2. We're multiplying the exponents. Okay. We can even do this with a general term. -1 to the n, x to the 4n divided by 2n factorial. Okay. This is a thing that we can do. Okay. Next, I've got write me the Maclaurin series for sine x over x. All right, now this one's a little different because it's not like I'm not replacing x with anything. Okay, so start with what you know. We don't know a Maclaurin series for 1 over x. We do know a Maclaurin series for sine of x. So, sine of x is equal to x minus x to the 3rd over 3 factorial plus x to the 5 over 5 factorial minus x to the 7 over 7 factorial all the way up to -1 to the n plus 1 x to the 2n plus 1 over 2n plus 1 factorial, if we're starting at 0. Right? Well, if I wanted to get sine x over x, that's like multiplying by 1 over x. Okay, so 1 over x multiplied by sine x would be 1 over x times x minus x to the 3rd over 3 factorial plus x to the 5 over 5 factorial, and so on. I can even distribute this to the general term. I forgot to put dot dot dots after the general term because it's going to keep going. And okay, so this is negative 1 to the n plus 1. I'm just copying. All right, and we're just going to distribute that in. We're familiar with the distributive property. Just take it to every term. So that's going to be x divided by x is 1. X to the third divided by x is x to the 2. Wait, I didn't divide. Yeah. X to the 4 over 5 factorial, so on, plus negative 1 to the n plus 1, x to the 2n plus 1 divided by x times 2n plus 1 factorial. Now, what we were doing each time was effectively reducing the power by 1, right? And so what I could do is I could just, cancel like that and reduce the power by 1. That is an option. Or you could write it as it was. But we need to be able to recognize that they're both the same. Just a side note for anybody that took calculus AB or that just happens to be interested in the limit as x goes to 0 of sine x over x. It's one of our special trig limits that we unfortunately didn't have time to do in the first semester. We did it with L'Hopital's rule, and it was really easy. But, sometimes that's an important limit for building up certain derivatives and other things that we had to skip over because of time. But if you look at the limit as x goes to 0 of sine x over x, right, that's going to go to 0 over 0. But in terms of the Maclaurin series, it's going to be 1 minus 0 plus 0 minus 0 plus 0 minus 0, and so on. So we can see that it's going to be 1. And I really like that. I think that's a nice thing that's like kind of just like jumping out at us from the Maclaurin series. And then I'll also use the Maclaurin series for sine and cosine after the AP exam to show you all about how e to the I pi plus 1 equals 0. That's another really easy thing that will just kind of fall into place if we use the Maclaurin series. All right, next I want y'all to write me a Maclaurin series for e to the x minus 1. I'll start off with the sum for the Maclaurin series I said that wrong. The Maclaurin series for e to the x. E to the x equals the sum from 0 to infinity of x to the n over n factorial. Now, y'all write me, I'm going to freeze the screen, y'all write me the polynomial for e to the x, and then subtract 1. And if you're watching at home, you should pause the video because it's just going to flash up with the answer here in a second. All right, there you go. So we know that e to the x is 1 plus x squared over 2 factorial, x to the 3 over 3 factorial, x to the n over n factorial. And if I wanted to subtract 1, well, I would just lose that 1 at the beginning, right? That's all that's going to happen. I'm not losing any powers of x or anything. So I just lose that 1. So I have x plus x squared over 2 factorial plus x to the 3 over 3 factorial all the way up to x to the n over n factorial and beyond. Now, my question for y'all is, how would I stylize this in sigma notation? Because isn't the general term still the same, x to the n over n factorial? Any suggestions for how I could deal with this? Yeah, start the index at n equals 1. That's interesting. Really had to encourage them for that last year, and I guess y'all just saw it. Okay, now, that's just, I don't think that's going to be super important for us, but, something good to talk about. So I'm going to erase that, and I'm going to ask you to give me another one. Maybe I'll ask you for e to the x minus 1 divided by x. So again, I'm going to freeze the screen. If you're watching at home, pause the video, and I'll show you the answer here in a second. Okay, there we go. So all I did was I distributed a 1 over x, or divided each term by x, which effectively just reduced the power by 1 on each term. Okay, and then we can see that in the general term, because basically what we have is, maybe I'll just write this as x to the n divided by x times n factorial. But you can cancel, same base, different exponents. That's x to the 1, so we just reduce the power by 1. All right, the next one I got for you is a very challenging problem here. So, you've made it to Cal BC, you made it through the first semester. You definitely know how to FOIL, right? We're good at FOILing. We can probably even multiply two trinomials using the box technique or just using our own cleverness. But have you ever multiplied an infinite degree polynomial by an infinite degree polynomial? And I suspect you haven't. And I don't know, this might be a bit of a letdown because we're only going to write the first three non-zero terms. Okay, what I'm going to do is I'm going to say, okay, sine x over 1 minus x. Okay, I feel like if we just use the first three terms of each of these, then we'd be ready to FOIL. Or it's not going to be FOIL, it's going to be just a large distribution. Okay, so I'm going to say sine x is x minus x to the 3 over 3 factorial plus x to the 5 over 5 factorial, and so on. Multiplied by 1 over 1 minus x is the geometric one with first term 1 and common ratio x. What I'm going to do is I'm going to actually set up using the box technique. Again, thank you to Miss Metz for showing me this a couple of years ago when I was teaching Algebra 2. Not sure, I think I just drew a bunch of rainbows and it got really crowded. Or maybe I did some sort of like tiered system, but we're going to also notice the lattice method. So we're going to, I'll just put 1 plus x squared and dot, dot, dot. Horizontally, I'll put x negative x to the 3 over 3 factorial and positive x to the 5 over 5 factorial. And you can imagine, well, maybe there is enough room in my window. I can just put dot, dot, dot right there. And it would just keep going. Well, it's not that bad. Don't be complaining over there, 141. All right, so 1 times x is x. 1 times negative x to the 3 over 3 factorial. 1 times positive x to the 5 over 5 factorial. Then distributed in x. I've got an x squared. I've got a negative x to the 4 over 3 factorial. And a positive x to the 6 over 5 factorial. Then I'll distribute in x squared. And I'll have x to the 3rd minus x to the 5th, minus 5 powers of x, over 3 factorial. And positive x to the 7 over 5 factorial. And the thing is that we need the first three non-zero terms. So looks like there's no constant term. But if you plug in, it's a Maclaurin series, so f of 0 would be the constant term. Plug in 0 to sine x over 1 minus x, and you get sine of 0 divided by 1, which is 0. Okay, well, that's a 0 term, so we want the first three non-zero terms. Okay, first we're looking for first power terms of x. That's just x. Right, then second power terms. Okay, I'm only seeing the one second power term right there, so I'll just add in an x squared. And the third power terms. Now I see two of these, so I'm going to use them. I see x to the 3rd here, and I see negative x to the 3rd over 3 factorial. Okay, we can combine these. And do a little factoring. And those are the first three terms of the Maclaurin series for sine of x over 1 minus x. Okay? And that is, I'll tell you, that is as difficult as these manipulation problems are going to get. Okay, the last manipulation problem I have for you is something that I find to be very interesting, pretty useful. write me a Maclaurin series for the antiderivative of e to the x squared with respect to x. Well, e to the x squared is one of those functions I've told you throughout this course has no closed form antiderivative. And that's where the closed form comes in, right? That's the kind of the fine print. It's like, okay, I'm going to write you down an antiderivative for e to the x squared right now. It's just going to be a polynomial. It's going to be an infinite degree polynomial. And that's all right. It's pretty useful. Okay? What I'm going to start off with is, well, what do y'all think I should start off with? I don't know that much about e to the x squared. I don't have a Maclaurin series for it. What do I have that's close? Yeah, okay, I'm going to start off with e to the x equals 1 plus x squared over 2 factorial, and so on. Okay, e to the x squared is 1 plus x squared plus x to the 4 over 2 factorial plus the rest of them. And then the antiderivative of e to the x squared with respect to x, well, I know how to take the antiderivative of polynomial. It's very easy. There's going to be a plus c plus 1x plus 1/3 x to the third plus 1/5 of x to the 5th over 2 factorial, and so on. If I needed to write the general term for this, I'd be best off having the general term for the earlier ones. Okay, don't just try to figure out what this is. That looks hard, right? I'll show you the easier way to do it. This is x to the n over n factorial. We replaced x to the x with x squared, so that'll be x to the 2n over n factorial. And what I'm going to do is I'm going to increase the power by 1, right? Divide by the new power. And then I still have that n factorial in the denominator. And I've got this plus c. Okay, so I'd be able to do some work if I had some sort, if it was a definite integral, I could, do some work and figure out what that plus c was. If I had an initial condition, I could definitely find that out as well. Something like that. Okay, the last kind of skill I'm trying to build today is how do we recover info about a function given its Taylor series? So I'm going to first start by writing down the general form for a Taylor series. Okay, so the general term for a Taylor series is the nth term has the nth derivative, n factorial, and the nth power of x. Okay. So what if I gave you a Taylor series, okay, so t of x equals 1 minus x, maybe plus 3x squared, minus 6x to the third. And I tell you that's the third degree Maclaurin polynomial for f of x. And then I asked you to recover some information about the function. Like, for instance, what's the value of f triple prime of 0? Well, okay, you take the thing, if you want the third derivative, you want the third power term, not just the third term, because remember, the nth derivative goes with the nth power. Okay. The factorial isn't always as reliable, right? I don't see any factorial numbers there, so I can't rely on that to, connect my nth derivative to which term. Okay, you think nth derivative, nth power. Okay, so over here, I know that negative 6x to the third is equal to the third derivative of f at 0 divided by 3 factorial times x minus 0 to the third. Well, I've got these x to the thirds on both sides, so obviously the x to the third is not contributing to my derivative. I already know that based on how the Taylor series is cooked up. So that means that f triple prime of 0 has to be equal to negative 6 multiplied by 3 factorial. There will be plenty of practice on this on the homework and stuff. All right, my next question is the function concave up or concave down at x equals 0? If you hear me ask you about concavity, what are you thinking? Second derivative, yes, for sure. Okay, so I really need to know what is f double prime of 0. That's really what this question is asking. And then we'll determine is it positive or negative, and from that we'll determine the concavity. All right, well, if I want the second derivative, I need the second power term. Okay, so 3x squared equals f double prime of 0 divided by 2 factorial times x squared. Okay, well, these x squareds are not really helping me, so I can just kind of divide both sides by x squared. And I'll say that f double prime of 0 is equal to 3 times 2 factorial. And I feel like, I said that the third derivative was negative 6 times 3 factorial? Is that what we said? Okay, I just felt like I'd said 3 times 2 factorial before. Okay, this must be calculus deja vu. And, all right, that is a positive number, meaning f is concave up at x equals 0. All right, and I've got another one of these, but I'm going to actually start with, lost my place. The bell rang. I was saying goodbye to people. Okay, so find the coefficient of x minus 1 to the 10th. Okay, well, I know that that will be, from the general term, the 10th derivative of f at 1, 10 factorial x minus 1 to the 10th. Well, that's going to be, the 10th derivative is 10 plus 2 is 12, over 10 plus 3 is 13, times 2 to the 10, who knows what that is, times x minus 1 to the 10th. Okay, but what have I forgotten? I have the derivative, I have x minus 1 to the 10th, I do not have my 10 factorial. Okay, so this really ugly number that I am highlighting in yellow is the coefficient of x minus 1 to the 10th in the Taylor series for f of x. All right, the last example I've got for you is, here's a different Taylor series for some function around x equals negative 3. Determine if a relative maximum, a relative minimum, or neither at x equals negative 3. So remember, when we're trying to determine maximum, minimum, or neither, we need to either do the first derivative test or the second derivative test. Okay, but the first derivative test, I don't really have any information about what's going on outside of x equals negative 3, just what's happening at x equals negative 3. Okay? So what I'm going to do is I'm going to just try to figure out what the first derivative is and the second derivative is. Okay, so f prime of negative 3 times x plus 3 divided by 1 factorial is equal to, well, 0, right? There's no first power term, meaning that f prime of negative 3 has to equal 0. I'm going to do some similar analysis on that x squared term. Negative x plus 3 squared is equal to the second derivative of f at negative 3 divided by 2 factorial times x plus 3 squared. Okay, meaning that the second derivative of f at negative 3, I would multiply both sides by negative 2 and cancel off the x plus 3 squareds, would be the negative of 2 factorial, okay, which is less than 0. So if we're flat and concave down, that means we're at a relative maximum. And that's all I got for you.